Good day everyone, welcome back to another lecture series. In today's video, we are going to go through the topic of dynamics. Dynamics, which is derived from the word dynamis. In Greek, it means strength, power, fortitude, or we can simply understand it as being a force. So you can straight away tell that this chapter is going to be talking about forces and basically how forces will cause motion and how we can use the motion of an object to determine the force acting on it. So that is the entire coverage of this whole chapter. Let us start by defining what a force is. Now, a force is just a push or pull. So if I'm pulling onto a rope, I'm exerting a force on the rope. If I'm pushing on the wall, I'm exerting a force on the wall. Regardless of whether the wall moved or not, I did exert a force on the wall. That is the force. There are two types of forces, and we classify them under contact forces and non-contact forces. Contact and non-contact is quite simple to understand. Contact just means there is contact, like you are actually touching the force. Examples include your frictional force, your normal force. For normal force, there is contact. Your tension. You have to physically pull onto the rope. You have to touch the rope. So that's contact as well. And air resistance. You might ask, for air resistance, you don't have any contact. But you do. Okay? You do have contact with the air molecules when you collide into them. Then we have non-contact forces. Non-contact forces are like your gravitational force. You don't have to be touching Earth in order to feel the effects of the gravitational force. Even if you're in space, for example, the International Space Station. The International Space Station is very far away from the surface of the Earth, but it is still experiencing the gravitational force from the Earth. It means that you don't need to have contact in order to feel the force. Okay. Another very similar concept is your electrostatic force. Electrostatic force is the attraction or the repulsion due to two charged bodies. Okay, so if, for example, if I have a positive charge and I have a negative charge, there will be an attraction. This is the electrostatic force. If I have a negative charge and I have a negative charge, there will be some form of electrostatic repulsion. That is also part of your electrostatic force. Next, we have your magnetic force. Magnetic force is quite simple. We experience this since we are young, when we play with magnets. So magnet, right, when you put them together, unlike poles, they will attract each other, and like poles, they will repel each other. So that force doesn't require any form of contact. The next concept we want to talk about is mass. Okay, so mass is just the amount of matter in a body. By matter, in the O levels, we mean solid, liquid, or gas. Alright, that is matter. If I have a lot of matter, then I'm very massive. My mass is very large. If I have very little matter, my mass is very small. Take note that matter and volume, they are two very different concepts. So something can be very large, but it can weigh very little. Okay, it can be very non-massive. It can be very light. For example, the air in your room takes up a very large volume. It occupies the entire room. But the mass of the air inside your room may not be that large. compare this with, let's say, what I have in front of me, a computer screen. Now, this computer screen may occupy a small space in the room only, but it might be more massive. It might have more matter within it than the air around me. So that is mass. Next, the next concept is on gravitational field. Gravitational field. When we say field, right, you think of field as a region of space. And when we say gravitational field, it just means that it is a region of space where a mass experiences a force. So, formally defining it, it's a region of space in which the mass experiences a force. Okay, that's about it. When we want to measure how strong a field is, we are going to use the term gravitational field strength. Gravitational field strength. So gravitational field strength is a measure of how strong that gravitational field is. What is gravitational force affected by? Well, it's affected by the mass of your body. For example, the thing that you want to attract. And it's also affected by the mass of your celestial body, like Earth. Okay, if you compare two different planets, Earth and let's say Neptune. Neptune is much larger than Earth. So Neptune will have a larger gravitational field strength than Earth. Another comparison is between Earth and the Moon. The Earth is much more massive than the Moon. In fact, the Earth is about 6 times more heavy than the Moon. This means that the gravitational field on the Moon will be 6 times weaker than Earth. That's why you see people doing moonwalk. Okay, you see people doing moonwalk. When people make a jump right on Moon, right, it will appear as if they are floating. It will take much longer for them to hit the ground. Okay, so the gravitational field strength on Earth is 10 newtons per kg, and then the gravitational field strength on the Moon is around 1/6 of that, so 10 over 6, which is, let me just get my calculator and we can figure out this number, 1.67 newtons per kg. Do you need to memorize this number? You only need to memorize one, which is 10 newtons per kg. Okay. Now, let's talk about another very similar concept to mass, which is your weight. I'm going to write it here. Weight. Weight and mass, although in our daily lives they are used interchangeably, but they are in fact two different concepts altogether. Weight is the amount of gravitational force exerted on a body, whereas mass is the amount of matter. Take for example, me, my mass, right, is determined by the number of molecules that are residing within my body. This is the same whether I'm on Earth or I'm in space. The number of molecules, assuming that no molecules leave, will be the same. So I have the same mass on both Earth and in space. However, for weight, right, weight is dependent on the gravitational field strength. The stronger the gravitational field strength, the larger the gravitational force, and that means larger weight. Gravitational force is weight. So let's write this down. Weight is the amount of gravitational force acting on a body. The reason why most of us would use weight and mass interchangeably in our daily lives is because the gravitational field strength don't change by much when we are moving along different parts of Earth. Okay, so let's say my mass is 70 kg and my weight is 700 newtons. This 700 newtons will stay the same whether I'm in Singapore or I'm in USA. It will be roughly the same. Yes, it might differ slightly because of a lot of different other factors, but it's roughly the same. So we use them interchangeably. Now, weight actually changes drastically if we move further away from Earth. For example, if we take a rocket and we fly out of the Earth's surface, then your weight will be changed drastically. Okay? When you reach a certain distance, far enough from Earth, right, you will appear to be weightless because the gravitational force acting on you by Earth is so weak that you don't feel the effects of it. Alright, so mass is, the SI unit is kg. Weight SI unit is newtons. Weight is dependent on gravitational field strength, on G. This G is gravitational field strength. Okay, I forgot to introduce this formula to you guys, which is G equals to W over M. The gravitational field strength is weight divided by mass. So weight is dependent on G, whereas mass is not. Weight is measured with a spring balance. A spring balance is, as the name implies, is something with a spring inside, and then there's a hook here, and it measures the amount of force applied on this end. Okay, assuming that the top end is fixed, it measures the amount of force that's exerted on the bottom end. Okay, this is in contrast to mass, where we will be using electronic balance to measure it. Okay, so this is it looks like this. Just a platform, and then you put a dish, and then you put whatever you want to measure on it. Then there will be a reading right in the middle. Okay, mass is also a scalar quantity. It's a scalar quantity because it has no direction. Whereas weight, right, is a vector quantity because it's a force, and forces do have direction. Okay, next one, we will talk about Newton's 3 laws. These 3 laws are the founding principles or the founding concepts of whatever we are learning today. Let's write down the Newton's 3 laws. For some laws, it's important to define, whereas for others, it's not that important to define, but more important to understand. Let's talk about the first law first. The first law states that when a body at rest will remain at rest, comma. Okay, this one sounds stupid. It sounds stupid, but there's actually a lot of deep meaning behind this. Okay, to us it sounds intuitive, but when you apply it to a physical object, it may be very different. So don't take it lightly. A body at rest will remain at rest. That's the first part. A body in motion will remain in motion in a straight line. Okay, it will move in a straight line at constant speed. When you move in a straight line at constant speed, it just means that you have constant velocity. But we try to be a little bit more precise. A body in motion will remain in motion in a straight line at constant speed, comma. This is not without any conditions, unless acted upon by an external resultant force. Let's slowly break down the last three terms. What is external resultant force? External means not belonging to the system. And resultant just means the vector sum of all forces. Let me give an example. Let's say I have a block. Okay, this block is floating in space with a velocity v. if we don't do anything to this block, if there's no force applied on this block, then the block will continue to move at V forever. But let's say it comes near Earth and it experiences a force here. This force will cause the box to deviate from its original path. So it will no longer be moving in a straight line at constant speed. In fact, it will start to accelerate down. That is something that we must know. Okay. What do you mean by external? And what do we mean by resultant? External means not belonging to the system, and resultant just means the vector sum. Okay. When you're falling down onto Earth, maybe perhaps you would have some air resistance that are acting on you. These air resistance will actually reduce the net force. So our net force will still be downwards, but it will be at a smaller magnitude. Okay. The net force is what determines the acceleration, and ultimately it will result in the change in velocity in that direction. The second law is, we don't have to define it, but we can just say that it's F equals to ma. Okay, this is the law of acceleration. The previous one is law of inertia. Okay. The first law tells us whether the object will... the first law tells us how the object will move. Whether it will move in a straight line or whether it will be accelerated in certain directions. This is about how. Okay. The second law tells us at what speed or at what acceleration this will move. That's why the formula is very important, because given a certain net force acting on a mass, there will be a certain acceleration on the object. And with this formula, we can calculate exactly the magnitude of the acceleration. Okay, so let me introduce you to another term as well, inertia. Inertia is dependent on mass. Okay, it depends on mass only. You can think about two objects, an elephant and a mouse. Which one has more inertia? Okay, regardless of what's happening to both of them, the mouse can be moving at super fast speed, the elephant could be stationary, but the inertia will just be dependent on the mass. So the elephant will always have a larger inertia. Inertia, formally defined, is the reluctance of a body to change its state of motion or rest. It would definitely be more difficult to stop an elephant from moving than to stop a mouse from moving, no matter what speed they were initially moving at. Okay, so that is inertia. Okay, third law is the law of action-reaction, which states that if A exerts a force on B, then B will exert an equal but opposite force on A. Okay, equal and opposite. That's why you see the minus sign here. This minus sign denotes that the forces are opposite. Let me give you a simple example. If we are pushing onto this box in this manner, the force exerted by us on the box is, let's say, 10 newtons. Okay, this 10 newtons is the force exerted by us on the box. The box will exert an equal but opposite force on us, which is also 10 newtons. Okay, so there are 4 conditions for us to classify two forces as action-reaction pair. The first force, the first condition, is that they must be equal in magnitude. Okay, so this is equal in magnitude. They are both 10 newtons. The second condition is that they must be opposite in direction. The force exerted by us on the box is 10 newtons to the right, whereas the force exerted by the box on us is 10 newtons to the left. So these are opposite, which fulfills the criteria. The third condition is that they must be of the same type of force. The force that we're exerting on the box, right, is actually a type of normal contact force. So similarly, the force exerted by the box on us must also be a normal contact force. Number 4, the forces must be acting on different bodies. So you can see that for the force exerted by us on the box, right, this blue color force is on the box. But for the force exerted by the box on us, this orange color force is on us. The two different forces are acting on different bodies. One is on the box and one is on us. So that also fulfills the criteria. Which means if these two forces fulfill all 4 criteria, we can classify them as an action-reaction pair. Very, very important concept, because think about how your rockets are flying. Okay, your rockets are flying because the rocket pushes air out at a very large speed. So this is the force by rocket on air. It expels a lot of air in a very short period of time, causing a very large force. The air will also exert a equal and opposite force on the rocket, and this equal and opposite force is what causes the rocket to be propelled upwards. Okay, so it's important, like what you have seen me do here. We are drawing a lot of free body diagrams. That is important to solve all dynamics questions. Draw free body diagrams. Okay. There is another part which is on vector diagram. I think this one we have already covered in the first lecture. So if you have not seen the first lecture video, go down to my channel and you can watch it from there. There's 2 other concepts that I want to talk about. Number 1 is the effects of friction, and number 2 is terminal velocity. Well, the effects of friction are quite simple. These are just quite common sense stuff lah. So friction is useful in some way and it's not useful in some way. For example, friction allows us, this is a positive part, it helps us to create motion. Without frictional force, we cannot move. We cannot even walk on the surface of Earth. Okay, think about how it is like to walk on ice. Sometimes it's very slippery because the friction is very little and it's very hard to walk on ice. If you drive your car on ice, then your car will have a hard time moving. The wheels will start to skid because there's no friction. So friction is important because it helps us to create motion. Your roads, they are very rough because it's to provide enough friction for the cars to brake as well as to move. So it's important to build the roads correctly. Now friction also helps to slow us down. For example, when we are jumping off the parachute, okay, we are jumping off a plane like a skydiver. How does the skydiver fall? He needs to use friction, which is a type of air resistance is a type of friction. So he needs to use some air resistance to actually slow him down so that he can land on the ground at a safe speed. So that is also another positive thing. I will just share another downside and then we will go on to the last portion. So the downside of friction is wear and tear. Because there's friction, our tire grooves, the grooves on our car tires will get worn out and we need to replace them regularly. So that is the downside. But of course, there's no choice. There's no choice. We need to replace them because we are making use of friction for movement. The last concept is on terminal velocity. Well, terminal velocity, a lot of students are very confused by this concept, but it's quite simple. Let's imagine that you are jumping off a plane and you're just jumping. You just leapt off the plane. At this particular instant, your velocity is 0. Okay, we are talking about that instant that you put your foot out the door. That instant. Because you're not moving, the only force that's acting on you is the gravitational force. Okay, and we can assume this gravitational force to be constant. I know that it actually changes with the altitude, but the change is very negligible. We can assume it to be constant. Okay. And because there's a downward step force due to your weight, you are going to start accelerating downwards. Okay, so acceleration is downwards. As you accelerate downwards, your velocity will increase. And then you are going to crash into more air molecules. There are air molecules in the way, and you are going to crash into them because you're moving fast. So these air molecules will exert a force on you upwards. This is called your air resistance. Your weight stays the same in magnitude. Because the weight is still greater than the air resistance, the net force will still be downwards. This is the net force. And you are still going to be accelerating downwards. It's just that now your acceleration will be at a slower rate. And as you keep accelerating, your speed is going to get faster and faster. You are going to crash into more and more air molecules, and that will increase your air resistance. There will come a point in time when your air resistance is going to be equal to your weight. At this instant, your net force will be 0. Net force is 0. And there will be 0 acceleration. 0 acceleration meaning your velocity will no longer change. Okay, so you're moving at a very fast speed with a constant air resistance and experiencing a constant weight, which results in net force 0. Because you have no more acceleration, you have reached your maximum velocity. This maximum velocity is also known as your terminal velocity. That's the final velocity that you have reached. If we are asked to explain such questions, we can talk about how the air resistance is now equal to the weight, and because of that, the net force is 0, and because of that, the acceleration is 0, and because of that, the velocity is a constant maximum, and that's how we reach our terminal velocity. So this is the underlying concept: the air resistance increasing over time. It doesn't just work for parachutes and parachutists. It also works for cars. Okay, sometimes cars, you are also experiencing air resistance, and then you have a constant driving force forward. So what is the maximum speed that you can reach in a car? Okay, the concept also applies here. But just know that it's because the air resistance or whatever resistance is increasing with speed. That's why you have terminal velocity. That's all from us today. I hope this video has helped you. Do help to subscribe to us. If you're keen to join our classes, we offer a free one-to-one trial class online. You can click the link in the description below to sign up for your free trial class. And I'll see you in the next video. Thanks everyone.